Okay, now, what happens though when we are titrating a weak acid or a weak base? Well, basically the initial thing is still stoichiometry. You're going to take into account what's happening in the reaction first. Then what's left over is going to, instead of being a direct pH calculation, it's going to be an equilibrium situation because you're going to have weak acid or weak base. Alright, so let's take a look here. Now we have 100 milliliters of 0.1 molar acetic acid by 0.2 molar potassium hydroxide. Okay, so we're going to take these step by step, and I've done some little tables here to help you out. So first, here's our BCA, before, change, and after. And I've already filled this in. Alright, so here I have, well, and actually this is when I've already started adding. The first one had you find the pH of the buffer, and that's before you've added the potassium hydroxide, or no, not the buffer, it would just be of the acetic acid. But you should already know how to do that. That's just finding the pH of the weak acid. So now, once we've started adding our titrant here, which is the potassium hydroxide, and I've color-coded in here what we care about. There's the hydroxide interacting with the acetic acid, and again, we're going to be making a salt with its conjugate base as we proceed through the titration. So we just use this to find what we have left at the end, and as long as at the end we have some of the acid and some of the base, then we can use Henderson-Hasselbalch to find the pH. Okay, so now the other thing though is, all right, remember how when we're using Henderson-Hasselbalch, we're using molarities. Well, one of the things to note is that, okay, so there we've added 20 milliliters. And what was our initial one? 100. So we really have, at this point, 120 milliliters total. But the thing to remember is that since in Henderson-Hasselbalch, all right, there's base over acid. Okay, so in here, if I do this, it's acetic acid. All right, now, what is the molarity of our base? This was in, 120. So the base is going to be 0.004 moles per 0.120 liters. And then the acid is going to be 0.006 moles over 0.120 liters. So when we're doing these kinds of titration problems where our acid and base, the volumes are, like our total volume here is going to be the same, this molarity, which it should be anyway. The total volume there is going to cancel out. So we can actually do the ratio of moles to moles when we're working in a situation like this. They're all in the same solution. The volumes are the same, so it's going to cancel. All right, so let's do, all right, this is going to be 4.74 plus, and then we want the log of 0.004 divided by 6, and I get a minus 1. Six. So 4.56 would be my new pH. Okay, so let's look at it with the next addition. So now we've added a little bit more of the base. Okay, but again, look at what's left. Okay, so here we're at where? We're at our halfway point. So our pH is going to equal our pKa, 4.74 from before, because we have the log of 0.005 over 0.005. So we're at the halfway point. So 4.74. Okay. Then now we are beyond the halfway point, but we're not quite at the equivalence point. We still got parts of our acid and base there. Okay. So pH is okay. And here at this point we are at the equivalence point. Alright, so there are 3 types of calculations you're going to do in any of these. If you are before the equivalence point, you can use Henderson-Hasselbalch because it's going to be a buffer solution. At the equivalence point, though, what have I got? I only have my conjugate base. All right, in this case. And now, since I didn't keep track of my volume, I'm going to need, because I will need the molarity here. So let me flip back just real quickly to see where I am, how much I've added. So we're right there. So I've added 50 milliliters of that too. So I have 150 milliliters is my total volume at this point. Okay, so I do need to know that, because what's happening here at the equivalence point, all I have is my conjugate base, which means I'm going to get an equilibrium set up here, and okay, meaning ice. So we have 0.01 divided by 0.15, so I'm getting 0.0667. It's the molarity there, 0 and 0. And my Kb for the acetate is 0.56 times 10 to the minus 10th, and that's going to be x squared over 0.0667, doing our simplification, and so that times 0.56, 10 to the minus 10, square root that, so I get x equal to 6.09, it's 10 to the minus 6, and that is the hydroxide because it's a base, and so I get a pOH of 5.22, which gives me a pH then of 8.78. Okay, so at the equivalence point, you're going to do just an equilibrium with the conjugate that will be present. Beyond the equivalence point, so now I've added, and I should have looked again. Okay, hold on. At this point, I've added 100. So my total volume at that point is 200 milliliters. All right. Okay, so at this point, I have 200 milliliters is my total volume. And look what I've got. I have excess of my strong base, and then I also have this conjugate base of the acid. But in a mixture like this, remember what was its Kb? Its Kb was like 5.56 times 10 to the minus 10th. Okay, very negligible effect. Okay, so when I'm comparing it to this strong base that I'm titrating with, I don't have to worry about the effect of that conjugate salt there. All right, so at this point, I'm going to do my OH concentration is 0.01 moles. That's how much I have left after the neutralization, and it's in 0.2 liters. So after the equivalence point, it basically becomes, again, just a strong acid or a strong base, depending on what you're titrating with, problem. So the pH then is going to be 12.7. Okay.